about performance and mainly focused on the microarchitecture. So when we talk about performance, we can improve performance by optimizing, and we can optimize on many different layers of the stack. You can optimize your application, write better code, choose better algorithms, choose maybe a faster programming language, make sure that your assembly language uses the least instructions possible. You can choose a fast instruction set on a fast processor, which has a good microarchitectural implementation, for example, running on fast hardware. I think the only one that you don't really have control over is the physics, which are the same for everyone. So we can optimize on many different layers. Now, for the course CASS, for the course CASS, well, these top two layers are not very relevant. This is you can do many things, and they are very important in terms of optimizing performance of an application. Often you should probably start at the top layer, but these are not anything that we should discuss in a computer architecture course. So you could choose a better algorithm with better time complexity, better space complexity. You could use techniques such as lazy evaluation, memoization. That's just some random techniques that you can use to improve your performance of your application. But this has nothing to do again with the architecture. What is, however, already a little bit more interesting for the computer architecture course is maybe this part, the programming language and the assembly language part. So we have been translating, after all, in this course, C code to assembly code. A compiler does exactly that. And if you did a good job, well, we don't really evaluate you on performance in CASS or on the performance of your own compilations. But a compiler does what you have been doing all semester when you were translating C to RISC-V. And a compiler, of course, one compiler can be better than the other one. And a compiler can perform optimizations. For example, if you're going to write a function, you could try this out. Write a C function that does a bunch of computations, but in the end, always, for example, don't let it depend on any parameters and on any global variables, so that the outcome of the function is always the same. If you would then compile this with an optimization flag with GCC, it would replace the entire function with a simple return statement of that simple value. For example, what GCC and other compilers will also do often is inline a function to avoid. So if you call a small function, it might be more efficient to just copy those instructions of the functions to the code instead of performing an actual branch. Stuff like that. There's many more optimizations. We're not going to go into too much detail there, but we're going to look at a few. The optimization that I have mentioned earlier, where you inline a function, for example, or where you pre-compute results of functions that you know will always return the same, those are not necessarily interesting from an architectural level. However, there are some optimizations that completely depend on your architecture and your microarchitecture. Some optimizations that a compiler can do that might not even work on one architecture and might work very well on a different one. So let's take a look a little bit first at some examples of these optimizations. We're going to take a look at loop optimizations. Now, I've marked all of these layers of the stack because you do loop optimizations in the programming language, or you can do them there. You can do them at compilation time as well. You can do it at source in your source code. So, but in the end, it often depends on stuff in your architecture or even your microarchitecture. And you'll get what I mean very soon. A first example of an optimization, which looks probably quite weird the first time you look at it, but it can work depending on your architecture again. This one would make no sense without caching, but with caching, in fact, you could do something called loop vision, which means you have this loop, for example. Here's our example loop, and there's two arrays. and you're storing values, or you're accessing basically memory addresses in both arrays. Now, this all depends on your memory layout, but what we do know for sure is that these 100 locations of A are next to each other in memory. This is an array after all, and for B as well. We don't know necessarily where A and B are related to each other, but close to each. Probably most compilers would put them next to each other in memory, right? So this loop will access first a value from A, then from B, then from A again, then from B again. It'll do that 100 times. When we rewrite this as follows, we can access first all elements of A and then all elements of B. And if you remember last caching session, there was a reason why caches work so well, and that's because this principle of locality. So locality principle said that when you access a memory location, often the memory locations close to that location will also be accessed, right? And the second loop vision is much more local in those terms, because these 100 A accesses are all going to be all next to each other, and then the 100 B access is going to be next to each other. So this will probably make more optimal use of your cache. Now again, this all depends on how your caches work, but often this rewrite will actually have an increased performance depending on your architecture. This is a way you can increase performance by rewriting code, and maybe this looks unintuitive because you're even executing more code, but the price of missing the cache and having to go to memory is a big one to pay, and so this is often a realistic optimization. Another one that has been debated as well is loop unrolling, and this is something a compiler will do. You have a loop here, and you're summing a data array, so you're accessing each element of an array, and you could rewrite this code just as follows, where you go step multiples of 4 instead of multiples of 1. What's the big difference between those two? If we compile them, well, the loop unrolling will have less jumps with less conditional branches, right? This one has to do one every iteration, check the value of I jump, check the value of I jump. This one has to do that 4 times less often. Now, this has a good effect on the pipeline. We will see this in the next slides, in the end of this presentation, whereby avoiding branches is going to be good for your performance, or branches are in general bad for your performance if you have too many of them. And you will have a lot less branches if you do this, but there have been instances recorded, you can look those up if you want, if you're interested, where these type of loop unrolling optimizations decrease the performance. So this can be due to all kinds of reasons, but it all depends on your architecture, on your microarchitectural choices. It depends. It is not necessarily looking at the amount of instructions you're executing, but also how fast are those instructions going to be executed. And the speed of the execution of instructions can be completely dependent, or is completely dependent on your microarchitecture and architecture. Another cool optimization is explained on the blog of Intel, well, on many places, but there's a nice explanation on a blog made by Intel, and so we're going to go over their explanation. It's a very nice one to grasp. And this is, of course, all in reference to caching. So assume you want to multiply 2 arrays together. And in this example by Intel, they say, assume you have a machine, right? And in this machine, you can input 2 numbers, and it enters the multiplication of those 2 numbers in a table. So let's say you want to create this table. Well, there's 16 cells here, 4 by 4. So you have to enter the coordinates. You have to reset after each enter. So you have to enter these coordinates, well, 16 times, and these one as well, right? Each cell has a coordinate pair, 2 coordinates. That's 16 per coordinate. So 32 times, if you want to do this full table, you're going to have to enter 32 different numbers. Now, assume now, so this is probably an order that you're going to go through. This is how we would do it with a for loop, the nested for loop. If you would go and compute this with the nested for loop, you would write 2 nested ones, and then you would keep I fixed and then variable and make j variable. And you would go through one row, the second row, the third row, the fourth row. Convince yourself this is what a nested for loop would do. But now assume that your machine can store two numbers. Basically has a cache of two numbers. Those two numbers are kept in there until you decide to flush them, replace them. Well, in this case, this would already help us a lot in this order. We could have the one here fixed in there, and we can store it as long as we're traversing the row. And then we only need to change it once. So now, instead of having to enter this first coordinate or this row coordinate on each cell again and again, it's stored, it's backed up. So we only have to enter all these row coordinates once. So this is 4 times you have to enter something. And well, the other coordinate still has to be done 16 times. You could do the opposite, but it's the same story, right? So you have 16 for one coordinate, 4 for the other. So you have 20 times you have to input a number. It's a lot better than the 32 already. This is an example of how well caching can work. But in this case, there is a better order of traversing this array. You might have already seen this. Well, if you go through the array like this, right? Then, well, you load first 1 and 2. And these stay fixed. And then you just input this one, this one, this one, and this one. And you have done half of the column. So, in this case, you had to enter these two numbers once. And then you had to enter all of these once. So that's 6 entries. And the same goes, well, then you have to go again, these two. And then only you have to vary these ones. So, in this case, you're going to end up with only 12. That's a lot better than 18. And this is a weird order of traversing an array. And you could look at code of loop tiling. And it's going to be something very similar. So you're going to traverse these arrays in a way that you are improving on the amount of times you hit the cache, basically. And these are all examples of loop optimizations, of stuff a compiler can do, or you can do yourself in your source code, if you have knowledge of how your cache works to improve the performance of your application. Time to go another layer down. Let's look at this instruction set architecture. What choices can we make here? What can we do here in terms of performance? So, and we'll start off with a question, an abstract question, or think about it. What would you prefer? Would you prefer to have a program with only a few instructions, or a program which is 10 instructions long, just an arbitrary number, but the instructions are executed slowly? So your program has 10 instructions, but the processor is executing them quite slowly. Or would you want a program that has 30 instructions, let's say, and it does exactly the same thing as this first program? These programs are equivalent, but their instructions are executed a lot faster than in the first case. What's your answer going to be? Well, I'm assuming you're going to ask me some more questions before you can answer this, right? Because this doesn't say anything. Because, well, the time of your program, that's probably the thing that you care about. How fast is my program done? And for that, you need to know how fast are these instructions, right? So when we look at the time of a program, we're going to say, or we can calculate this. So a program has a clock cycle. First of all, our processor, is running at a certain speed, the clock speed. So when your CPU, when it's executing instructions, it's driven by a clock. And the clock speed determines how fast instructions are executed. Now, every instruction, right, requires some number of clock cycles. It can be 1, but this can be multiple as well. We'll see this. So, when you have to choose here, you're going to look at, first of all, how much time is taken for each cycle. This is the clock speed of your program. Then, how many cycles does it take to execute one instruction? And then, how many instructions does it take to implement the program? And all of these parameters are going to be defining in terms of performance. And this question that I just asked you is you could say a debate or a different viewpoint. And this is a debate called RISC versus CISC, or reduced instruction set computer, where you have a lot of simple yet fast instructions, or a complex instruction set computer where you have a lot of instructions. They can be very complicated, but they can be slower to execute. And well, it's in the name, right? RISC-V, the instruction set architecture we have been working with, and was designed originally by the writers of your book, of your Patterson and Hennessy, I guess. I think it was Patterson, don't quote me on that, who designed RISC first. In any case, RISC has only a few instructions, and they are all meant to be executed fast. You don't have an instruction in a RISC architecture typically that, for example, adds a value to a memory location. No, you load the value from the memory location first, then you add with registers, and then you store again to the memory. While if you look at Intel x86, for example, probably the instruction set your computer is running on right now, this is a complex instruction set architecture. It has a complex instruction set computer. You have a lot of instructions. You will have the move instruction on Intel, does so many things. And you can have an add instruction that can add a value directly to memory. And you have a lot of different choices. But these instructions are a lot more complex. So there is a trade-off here, CISC versus RISC. And it's a very interesting debate. And there's advantages to both choices. Personally, I like the RISC design. It feels more clean. But I wouldn't be able to claim that one is better than the other. I don't think there is a definitive answer for this yet. Here's to hoping that RISC architectures will take over the world. But again, we will see what happens. So to make sure I wasn't mistaken, I just looked it up. And indeed, Patterson has coined the term RISC. He was one of the early developers of the concept of RISC. So it's not a big surprise that your book is now currently working with RISC-V. Old versions worked with MIPS, which was also a reduced instruction set computer. And he even won the Turing Award with this design in 2017 with development of RISC. So, I mean, if you want to listen to someone in terms of RISC, definitely listen to the authors of your book. You have a very high quality book there. Patterson and Hennessy's book is a real, well, how do you say, a book that everyone should have and read in terms of computer architecture. In any case, let's talk about the microarchitecture. And well, in your microarchitecture, there's also stuff you can do. The microarchitecture, the way you implement your instruction set, the choices you can make there. When you design a processor, you need to make sure that you speak the language of the instruction set. If you can create a RISC-V processor yourself if you want to, if you have the skills. And it can be many different designs, and you can make a very slow one, you can make a very fast one. You have many choices there. This is your microarchitectural choices that you will have to make. But you don't have any choices in the instruction set. That's defined by the RISC instruction set architecture, right? And now let's talk a little bit of some optimizations there. And we'll start with pipelining, which is probably one of the most important ones. Let's introduce this concept. So, first of all, let's look at a very traditional or naive way of executing instructions, a non-pipelined way. We can already say we can decode an instruction, or we can execute an instruction in multiple phases. Depending on which instruction it is, it might not need all phases, but in general you could say you have a first phase where you fetch an instruction from memory. You get the value of the program counter, you look in your memory and you see what code is stored there. Or hopefully it's retrieved from the instruction cache a little bit faster. But in any case, you're fetching your instruction from cache, from memory. And then you have to decode this instruction. You have to instruct your hardware what to do next, depending on what the opcode of this instruction was, right? That's decoding this instruction. Then you have to execute the instruction. You have to, for example, do the additions, do the shifts, do the comparisons. You will talk with your logical units, with your ALUs, and you will execute the instruction. And then you have your results, and your results could be written to memory. Now, this is, by the way, these phases are typical for a RISC architecture. That's what we're talking about now. Now, it could also be that you had a load instruction where you didn't have to execute anything, but you had to access something from memory. It also could have been that you had a store instruction that should have to access something from memory. So then you would have just this memory access here. Now, it could have been possible that your load and store did work with relative addressing, right? You provided a register, but you also provided an offset to this register. You wrote to 5 or to 4 T0, this address. So you did use your execute phase actually, but then to compute the address of your load or store. So you still use all phases. And then you do your memory access, and lastly, you have your write back. So it's possible that you have updated your registers, for example. You want to update the values of those registers depending on what came out of the execution phase, for example. So this is how you could divide instructions in hardware in multiple phases. And if we look at how a very simple processor would look, very simple single cycle RISC-V processor, what it could do was the following. It could, per clock cycle, execute one instruction. Instruction 1, do all of the phases. Instruction 2, do all of the phases. Instruction 3, do all of the phases. We've taken this design from the simulator RIPES, which we will use in a second in this video as well. And you can definitely use it in your exercise sessions as well. I very highly recommend it. It can give a lot more insight than simply doing the pen and paper exercises. So of course you cannot use it on the exam, so make sure you just understand everything what you're doing, but this can be a great help to get insight into how all of this works. So this is a very simple RISC-V processor, and we can see the different phases of execution, the fetch, decode, execute, memory access, and write back phases very well here. So let's draw some boxes and you can see them. So first of all, we have this instruction fetch phase, which will determine which instruction will be executed. And well, which instruction is executed is going to be determined by this input line, which I'm hovering now. And this is going to be the value of the program counter, right? Of course. But this value of the program counter is dependent on, it could be two values. It's a multiplexer, it could be set to 1 or 2. Either the previous value added by 4, when you're just executing normal instructions, or it could be that you had a jump instruction, and then, well, we will see all the way at the end when this jump is resolved, the new address will be written to this line, and the multiplexer will show this line, and then your PC is updated to a different value, and you're not adding by 4, but you're jumping to a new address, right? But then, once this is done, you know the opcode of your instruction. And then you pass it on to the decode phase, so that the instruction can finally be executed. And this decode phase, well, it's going to get the opcode. We know the opcode and the operands in the fetch phase. And the decode phase is going to decode this into sending the opcode. Depending on the opcode, it might have an operation using 2 registers. It could be 1 register, 1 immediate, right? Depending on what type of instruction you're doing. And it's going to decode this and then send it on to the execute phase. So in the execute phase, we have this ALU, which for example can do our additions. These are arithmetical and logical units. Your logical operations, your arithmetic operations, it's an adder, a shifter, and so forth. And we have this branching unit. And all of this will in fact execute the instruction. So the decode phase will be able to basically drive this execution phase to do the correct things based on what the instruction in the fetch phase ordered it to do. So let's say we had an add instruction with 2 registers. Then these 2 registers here would be selected from the register bank. So the operation, the initial operation and decode phase would have gotten indices depending on these registers. So each register had an identifier which is encoded in this operation, in this instruction. And then the output here would be the value stored in those registers. So you check your register file depending on the instruction, which registers you're in use. You have added 2 registers together and the values are written to these lines. And then assume we had an add instruction with 2 different registers. Well then, this ALU would be set to additions. To do additions, it would add the 2 input values, and then you have your output. And in this case, since we didn't have a store instruction, well, then this would bypass right here the data memory phase. Nothing would happen in the memory phase. The write wouldn't be enabled because we're just doing a regular addition, not a memory operation. And we would go to this write back phase. And if you had an addition and you stored the results of the addition of 2 registers in a new register, well, then you have this write back connected to your data in of your register. And that's how you could execute a simple addition instruction. on the simple single cycle RISC-V processor. If we think about, for example, a load or store instruction, well, you had your address resolution there. So this ALU would now be, well, in this case, you would have selected one register typically. You do store word T0, for example, add offset 0 from T1. Well, then you have to add 0, which would be one operand of the ALU, to the value of the register provided. And then that would be used as input for your data memory. And then the other register that you provided, so the store word T0, T1, then the other register that you provided that wasn't used for addresses would be used as input for the data memory. You had resolved the address using the ALU, and you store it in your memory by enabling the write back. And that's how you could do a simple load or store. And this is a bit of the point of RISC. Look at how simple this architecture is. Most of the instruction types we've discussed now based on this simple drawing. And maybe the first time you look at it, looks a bit overwhelming, but in fact, if you break it down, you can really get to know all of these lines and what they do, and they make a lot of sense, and it's quite simple. For a complex instruction set, it's going to be a different story. Here's the disadvantage, though, of the simple 5-stage, well, not about the 5 stages, but simply doing it this way, having one instruction per clock cycle. Well, that means per clock cycle, in every single cycle, your instruction has to go through all of these phases. Your critical path to execute an instruction is going to be very long. And if your CPU is going to be too fast, well, then you might skip a phase, of course. If you overclock the single cycle CPU, where the clock is so fast that not all stages are executed, well, then you're just going to have wrong results. So you're really limited by the critical path here, by your slowest instructions going through, and you cannot increase your clock speed by too much here. And there's another basic analysis, and that it's, well, what if we could divide this CPU? Because these different stages, they seem like they're quite independent from each other, and in fact they are quite dependent. They are a bit sequential. But if the first instruction is done fetching from memory and it's already in a decode phase, why not start fetching a new instruction? Why not divide, right, our CPU into different stages and then having these stages execute in parallel? And this is what pipelining is all about. Assuming now an instruction goes through 5 phases and each phase takes 1 clock cycle, then it's going to take 5 cycles, worst case, if it has to go through each cycle, 5 cycles for an instruction to complete. So let's compare a single cycle design with a pipeline design. In this case, in the single cycle design, the one that we saw earlier, we have our clock, and each clock cycle, we finish one instruction. Now in our pipeline design, whenever the fetch of the first instruction is done, we already start fetching our second instruction. And when that's done, we start fetching our third instruction. Same goes for the decode and all of the other phases. So let me move myself a little bit here. What you can see here in these two designs is that, well, our single cycle, the latency, so the time between the start of the instruction and the end of the instruction, in this case is 1 clock cycle, right? 1 clock cycle start, same cycle it ends. In the pipeline design, however, 1, 2, 3, 4, 5, the amount of pipeline stages. 5 clock cycles here before it finishes. Okay? And then the throughput, if we compare the throughputs of these, so how many instructions per cycle are actually finished? So when an instruction is finished, you look right here when the last phase is done. In this case, in a single cycle design, we have 1 here, 2 here, 1 per cycle. Each clock cycle, we finish 1 instruction. And the same is true, actually, for the pipeline design. Every clock cycle, we execute or we finish 1 instruction. It might take a while to get going. The first 5 clock cycles, we do nothing. But after that, if we can keep the pipeline going, every cycle, we are finishing 1 instruction. Now, what you might notice is that this clock cycle looks a lot, or this clock looks a lot shorter. And well, in fact, the clock speed of this pipeline design, since each step needs to do a lot less work, the clock can be a lot faster. It might not be 5 times faster, but it's going to be a lot faster. And if we then look at these other values, well, the throughput, isn't that what we care about most in terms of the speed of our program? Right? Because how many cycles are completed per clock cycle? If we can double the clock cycle already, in our pipeline design compared to the single cycle design, then we have double the amount of instructions we can execute. If the cycles are double speed of the pipeline design, then you're executing at twice the speed, the same program. Now, you will have, though, this latency issue. It will take longer starting instruction and before it finishes. And there is a problem with latency, instruction latency, or there is a big difference. So there is a difference in latency. And also there will be some hazards. But let's look first at this 5-stage RISC-V processor, how you could implement this. Now, here's a nice visualization of a 5-stage pipeline RISC-V processor. A little bit more complex than our previous ones, but you can still recognize the phases. And I'm right now in this RISC simulator, a very nice tool, which you will also are advised to use during the exercise sessions. It's a very nice tool. You can really see how instructions are executed. You can write a program, execute it on this processor, see all of the phases, see how all these lines interconnect, what values do they have. It's a really great tool to get to know exactly how all of this works. So experiment with this if you don't yet understand all of this. So let me maybe first start by showing you the single cycle processor we just discussed, and you can show it in action. We can see it in action. I've written this very simple RISC-V program where you load immediate T05, load immediate T16, add them together in T0, and translate it to actual RISC-V, because these are pseudo instructions. They're not even part, well, these first two are not even part of the RISC-V instruction set. They're pseudo instructions, and they're translated to instructions that are exactly the same, but all in terms of, in the philosophy of, let's keep the amount of instructions minimal. So to do the load immediate pseudo instruction, what you do is an addition with x0 of your immediate value, and that is the same thing as loading an immediate. It gives you the value 5 and 6 here, and you store it in this register. So this load immediate is implemented like that. And now let's look at how it's executed on the single cycle processor. So right here we will read the address, well, I guess the address 0, and then in the second so this is the address of the next instruction is going to be 8. But right now, so when we are executing the first instruction, the PC is going to be pointing to 0. And then it's already preparing for the next step, which is going to be 4. So you can look on these lines what the values are on each line, which is very nice. So during execution of our first instruction, this is sent to the decode. So this is going to be the encoding of our instruction 500293. As you can see, that's what's being sent here on this line. Yep, there it is. And if this is decoded, well, first of all, you're going to see some register selected. We have, this is our first register, and this is our second register. But wait, the second one isn't the register. So let's first look and follow this first register. So we select the register 0 with index 0. That's a 0 register. And we send the value and the output, and we send it right here to this multiplexer, which will send it to the ALU. So we're sending the 0 value to the first input of the ALU. Now what's happening with the second output? This is being sent, this is being sent here. So you have this opcode being sent here, and you have also this immediate, you also have this immediate decoder. So the immediate being read here is also 5. And what we can see here is this register output, the second one is actually ignored because the second argument in this case isn't the register output. So it might go to the register selection. You might read the register 5 here, but the output here is just not used anywhere. So because we don't have a second register. Instead, we use the output of the immediate, which we get straight from well, this immediate decoding. So this is encoded in the instruction itself. And that's the one used by this multiplexer. And this is at the value 5, that's at the value 0. So our ALU will count them together and give us the result of 5. So this will be on this line, our output. This is then being sent all the way to this write back phase, where it is going to be sent back to the data in, right? And write is enabled here. So we are going to write to a register. And what register are we going to write to? X5, and that we can see right here. So we can see very nicely how this addition instruction is executed. And next cycle is going to do another addition, and the last cycle is going to be a little bit different. Now we can see both registers are in fact being used because we have two registers added together. We're not using the immediate output this time. We're not interpreting this as an immediate anymore. In this case, it says that beef here. It's a fake immediate. It's not a real immediate. We are using the value of x6 and x5. And that will give us the value 11 stored in T0 after this instruction is done. 0xb or 11. That's a single cycle execution of this small program. And now let's take a look at the pipelined one. So when we are pipelining, we divide everything into multiple phases, as we said before. And when we execute, let's go do this very quickly first. We can see here is this instruction starts in the first phase, and then when I advance, it's in the second phase now, the next clock cycle. It hasn't been completed yet. So you can see here, these instructions are not yet completed. I think there is a way to display the different stages, but you can see this instruction is an instruction decode phase. Second instruction is the instruction fetch phase, but they haven't been committed yet. Right here, there are 0 instructions retired. There's not a single instruction that is already completed and has stored this value. And if we continue, the third instruction will also be fetched. And you see, well, each instruction is just executing in its own phase of the pipeline. Right now, add-I x5, x0, 5 is in its execution phase. So these barriers basically stop and synchronize. And now they keep the signal and send it out again. And so now we're executing here this addition. Remember from what we just saw in a single cycle one, we're going to be adding the immediate 5, which is going to be coming from here. To this value 0 from the 0 register, and we have this result, and then it's going to be written back. Now, there is going to happen something interesting, and maybe you've already seen this or spotted this. We are going to have a problem. So, right now, we want to add, well, we're storing now, or now we're in the memory phase here, which nothing's going to happen in this case for this instruction, and then now x5 is going to write back its value to this register. But now, when we look at this and when we execute this completely, we're going to see something interesting. Remember, the end result of our execution should have been 11 in x5 or T0. It's 0. It's not 11. This is just simply wrong. So is this processor wrong? Well, yes, in a way it is. You could say the processor is wrong, our program is wrong, our program is not aware of the microarchitecture. What has happened here is a hazard. So the problem is here that this load immediate loads a value 6 in T1, right? But look at when this load immediate is done. When is it committed? So right here, in between these two phases, it's committed. But that's before the last instruction can actually get this updated value. So we're using stale values. So if we are going to take a look at that in, maybe it's a little bit clearer with the slides. So let me show you in the slides. So this is what we call a hazard. Right, we have this problem. Let me move myself, whereby we have a read after a write. So assume, for example, these two instructions. The first one updates the value of the register value of T0 in the write back phase. And then afterwards, the next instruction, LWT1, needs this T0 address to fetch, needs to use T0 to fetch something from memory. The problem is, this T0 value to do this address computation needs to be available in the execution phase, while this is only written back to the register file in the write back phase. So as you can see, this is happening earlier in time. What we have here is a read after write hazard or dependency. The new value of T0 is only available here, but it was already needed here. And we can solve this problem by forwarding. We can basically cut through the pipeline and skip a few steps. What you can do, you can analyze and see the following. With forwarding, you can see that add-I T0 to 01 here, when it's done executing, this result of T0 can already be sent to the execution phase immediately of this load instruction afterwards. It's already available here. This mem instruction is not doing anything here. It's not used. And you don't need to wait for the write back in this case to send your updated value right to LW. So you could have logic that forwards this value. Immediately when it's updated from the execution phase, it already forwards this to this new second instruction. This is what we call forwarding. And let's see that in action. So in our simulator, we can switch to this processor, which has forwarding and no hazard detection. We will get into that in a second. So this one has forwarding. And we don't see too many changes, but it's interesting maybe to put on the extended view here, where you can actually see there is this new unit called a forwarding unit. Now it's already a lot less clear what everything is doing, but what you can also see is there has been these two multiplexers right here added. You can see this is the main difference. We have this forwarding unit and these two multipliers. And let me quickly go to the simple view again, because it's a little bit easier to use and talk about. What's happening with these two units is these are basically inputs to your ALU. And when are they connected to? Well, if we're going to see, one is connected to the output of this execution phase. So this is sort of a short circuit, or however you would want to call it. Values from the ALU can already be in the next input in the very next cycle, as you can see. And this could be done with our additions. We can forward the result of our additions right back to the next phase. And so we don't have the problem anymore. And then you have this multiplexer, which needs to be controlled by this forwarding unit to choose, in fact, these new values instead of the values that were read from the register bank, which hasn't been updated yet. So that's a form of forwarding. The other forwarding that can be taken is this other branch, and this is just in case we need to forward memory operations, we need to wait until the memory phase is done, and after the write back phase, we forward immediately. So we can wait until before, so we can skip a phase here. We don't need to wait until it's updated in registers. We can already be using it right here. So that is how you can implement a form of forwarding. And now if we execute our very same program, now we're going to see that in fact, right here, we should see the forwarding units activate. So as you can see, this line is now activated, and we are reading the forwarded value when executing this instruction. We're reading the forwarded value of 5, and also we are reading the forwarded value here. So this is the value 5, the value that was in X5, it's forwarded, and the value right here is also forwarded. So in this case, it didn't even matter that there was no memory operation. This one we are forwarding 2 phases back, this one we are forwarding 1 phase back. And instead of computing 2 0 values, thanks to these two multiplexers right here, and these nice lines, and also this forwarding unit that has actually decided this multiplexers need to select these inputs, we are now ending up with a correct output. So we have solved our problems. There's a problem though. This is not always possible. This very simple example here, we have a load instruction, and we're loading from memory. T0 has got the memory index. So the address T0, we're loading this address from memory into the register T1. When is this result available? Only after the memory phase. What if you have this order of instructions? How are you going to forward anything if these are happening in parallel? It's not possible. If this execution phase needs the value of this memory, you just can't forward this. How can you solve this? This is a different hazard which we cannot solve. This memory phase needs to be completed. There's no good answer here. So what can you do? Well, this could be stalled. Now we're inserting a pipeline, bubble or stall, what you want to call it. We're stalling. We're executing a NOP instruction in between. We're doing nothing in between, and we are waiting. We're making this instruction take 1 cycle longer. This is of course not ideal for performance. Now, because of this, for example, some CPUs have done some optimizations in terms of, well, most CPUs, I think, high performance CPU, do stuff like out of order execution. They try to reorder many instructions to make sure these types of things don't happen, or to minimize them, because this costs us just an entire cycle is wasted here and every execution phase. So we don't want this. And you could wonder, who should solve this? Because, well, yes, your architecture could solve this, but you could also solve this with a compiler. And both have been done in the past. There was this variation of a MIPS processor that, well, that basically ignored these types of hazards and required the compiler to do this. But apparently, by having the compiler emit a bunch of NOP instructions, this had an effect on the instruction cache. There were a lot of NOPs cached, and your instruction locality is decreasing because you're executing relevant instructions. You're getting more cache misses in your instructions, and it was very bad for performance. But you can choose to do both. And well, the nice thing is our simulator actually does both. So let's take a look. So let me show this in action. And I've decided to load the value t0 from address 0. To let the value at address 0, which is going to be this code here. I'm loading into the t0 and I'm adding it by 4. And let me first show you just on a simple single cycle processor, which doesn't have all these problems, what the output should be, the correct one. Then we run it, and it should indeed be 2287, which is 2283, which we get in the first step, added with 4. That's the correct output. Convince yourself of that. Now let's switch to our CPU, and let's run this, and let's see what we get. Wait, now T0 has the value 4. So what has happened? It has added incorrect values. So our load has not loaded a correct value. Our addition has used a stale value and is adding together 0. Let's see what is adding together here. The addition is adding together 4 and 0. And what should have happened is the addition should have added, well, of course, the value that was loaded into register X5, but this value is not available yet. Only next phase it will be written to the registers or forwarded. So this is not possible. It's still being read from memory, so it cannot yet be used here in the ALU. Right. And how can we solve this? Well, we could insert a NOP here. Let's try this. This should work. So if we insert a NOP, we refresh and we run, we have the correct value. We inserted a NOP and we fixed our problem. This is what a compiler can do. Insert a NOP. No operation, that means. So now we have a very nice working solution. And now you see this is actually updated and well, the memory is read. And now, in fact, it can be used right here. And instead of 0, this is now 2283. But let's remove our NOP again. And let's look at the alternative. And that's fixing it in hardware. Then we have this 5-stage processor here. And we can look at the complex implementation here. It's going to detect these hazards. And when it detects the hazard, it's going to do the NOP insertion himself. So let's see that in action. So if I run this completely, first of all, we're going to see the correct value. How did it do that? Let's look at the different phases. Oh, and you already saw it when going backwards. So it detects a hazard right here. And what does it do? It stalls this instruction. It inserts a NOP here, as you can see. This is inserted by well, your hardware. It detected this and it automatically stalled the processor for 1 cycle. And then we have our hazard unit. So you can choose to do it in hardware or in software. The software implementations in the past have proven to be, well, less than ideal for caching reasons, but you can solve it both ways. The last problem I want to discuss, and that's actually a very important one still, is branches. Look at this simple program. We move 0 into T0. We then execute, so you know you can encode this as an add immediate of 2 0 or add as 2 0 registers together with a T0, or as an add immediate of 0 and a 0 register. You can choose. I'm not sure what the simulator will choose. But then you can branch, and in this case, well, the branch will jump to label. But simple processors, typical simple RISC processors, well, what I will just decide to do is assume for the pipeline that the branch won't be taken. So you can make 2 choices, right? You have to prepare something in the pipeline, but you need to, before you can, well, you can only decide in the execution phase here, after the execution phase, if the branch will be taken or not. So how can you know what to prepare in the pipeline? And so you need to make a guess. In advanced architectures, you use a branch predictor, which is a piece of hardware that is going to be, for specific branches, going to train itself to accurately predict the correct branch and place those on the pipeline. But, of course, these instructions here in the pipeline, if the branch is not taken, these two additions right here, they should not be executed. If the branch in this piece of code, they might be in the pipeline, but they can never be committed. So they need to be flushed before they can ever reach the end and be written back, right? So this needs to be detected and this needs to be eliminated. Okay, let's see this in action in our simulator again. So let's see how this simulator deals with it. I've taken 5-stage. I'll put the extended view on again. And let's see how this is executed. So here's our branch. So what we can see, our branch, there it is. This is the first instruction, loading 0 into x5. And here's our branch. Still, we don't know if the branch is going to be taken or not. Right here, we're determining whether or not the branch will be taken. And we will find out that the branch will indeed be taken, so that these two instructions are in fact wrong. x5 is t0, x6 is t1. That is not what should be executing. This is what's currently in the pipeline, but these two red instructions should not be there. And they're going to be evicted right here. As you can see, hazard unit detected and flushed these two instructions. They will never be committed to the as a result, and we waste 2 cycles. So as you can see, a branch is quite wasteful because these are two clock cycles where we're not going to be emitting any instructions. So this is bad for our throughput. If you remember all the way at the beginning where we're talking about loop optimizations, we at a certain point said branches can be expensive. This is one reason why branches can be expensive. You have to waste instructions in pipelines. If you cannot accurately predict what path of the branch will be taken, in this case, you will have to, in a way, flush some stuff from your cache and you're going to lose on performance. So that's quite, but because of this, we use the most advanced processor here, which detects this type of stuff, automatically inserts it. So it can be solved by hardware, but it's inefficient. Gonna end this presentation, the last presentation of CASS, with something I find somewhat cool or interesting. So these instructions that we crossed out here, the one that happened right after this branch instruction, these two, they were in the pipeline. They were never supposed to be executed. We canceled them just in time. But what if these instructions, while being in the pipeline, had some effect on certain states of the microarchitecture? So what do I mean? Imagine, for example, that these instructions were resolved, and imagine these were, for example, load or store instructions, not simple additions. And what if they had already been written to the cache memory, for example? And at a certain point, you decide to discard them, and you don't write the results to memory, but the results are already in the cache. So what if these instructions had an effect on the microarchitecture even though they should have never been executed? You might argue, okay, not a problem, because you never see the results of these instructions and your program still executes correctly, so there is no problem. Even though it might have had some effect on the cache, you don't read those values directly. You cannot access the cache directly, you cannot read from it, so it doesn't matter. And this was argued for many years, I think 15 or more years. And then a few years ago was discovered that this is actually a problem. So what this is called, these instructions are executed speculatively, right? In this case, the speculative execution speculated that the branch, so very simple RISC implementations will speculate, will say, this branch will never be taken. We will prepare the pipeline as though this branch will not be taken, and will always predict this. But a branch predictor might say otherwise. On a more advanced architecture, a branch predictor might say, well, I have watched the code and I've seen that this branch is taken. So this branch predictor could have been trained to actually start putting these instructions after the branch in the pipeline. In this case, we wouldn't have to stall because it accurately predicted the branch and we would have no performance loss. So that's a great thing, right? You have a branch predictor, and if it can accurately predict what the branch will do, well, then you don't need to stall your pipeline. Great. But what if you could, for example, train this branch predictor to mispredict? What if these instructions have effect on your microarchitecture. And all of this came together in a very nice attack. Apparently it is very dangerous. And this is called the Spectre attack. Definitely check it out. It's about speculative execution and how, in fact, the fact that these speculative executed functions that are instructions that are never committed to the actual architectures, the effects are not visible in memory, nor in the registers. They still had effect on the microarchitecture, in this case on the cache. Values were in the cache. And what you could do is assume there's a secret value after this branch, and the secret value is never loaded into memory. Well, you can get a secret value loaded into the cache if you can speculatively execute the instructions after the branch. Right? They are not, the secret value in these instructions is never stored into memory, or you cannot ever read it because it will be flushed way before that. But the cache has been affected, and they are living in the cache. And while you cannot read the cache directly, there are tricks now you can use, and certain speculative gadgets. So it's not going to be as easy as simply having a write of a secret here. But if this secret is an index in an array, and I'm not going to describe the full contents here. Well, but if it's an index in an array, you can determine what the value of that secret was. If the secret is being used as an index in an array, you can determine what the secret was based on what memory location was cached. If you know the cache layout and you know what index in the array was taken, then or what memory location was cached, you can derive from that what the index was. And if this index was a secret value, then you had a Spectre gadget. So a lot of explanation, probably not the most clear one ever given about Spectre, but definitely check it out. It's all about these instructions that are discarded still having an effect on the microarchitecture. And it's even worse in modern processors because, well, here's some pictures. Let me move myself somewhere. These pictures show that you just have very complicated pipelines on, this is an Intel Atom, in your smartphone, for example, 16-stage pipeline, which means, well, 16 instructions executing at the same time, just like in our 5-stage. So you have a lot more of these instructions executing at the same time. Pipelines can be very long, and they can have effect on the microarchitectural state. And this is a very active topic of research on how this microarchitecture can actually be harmful in terms of security. It's a very interesting topic if you are interested in this. Definitely look into the Spectre attacks, Meltdown attacks, Foreshadow, for example, developed by one of your, by Jovan Bulk, which is an assistant, who is going to be teaching CASS in the second semester as well. So right here at KU Leuven, much research is being done in this domain. If you're interested, definitely contact us. And that was the end of this presentation and the end of the CASS presentations. So hopefully you've gotten this far, and good luck with your exercise sessions and after that the exam.